Summary of Water Content Determination by the Karl Fischer Method and Introduction of Reagents. Karl Fischer titration was invented in 1935 by the German chemist Karl Fischer. It is an oxidation-reduction titration used to determine trace amounts of water in non-aqueous solvents, the reaction formula for which is expressed in two chemical equations marked by an orange-colored rectangle in the middle of this slide. Let me point out three key chemical compounds: iodine, I2, as an oxidizing agent, sulfur dioxide, SO2, as a reducing agent, and amines, abbreviated as base. Some typical amines that are used are pyridine, pyridine derivatives, and imidazole. The Karl Fischer reaction is an oxidation-reduction reaction which occurs when water, H2O, in the first equation, and methanol, CH3OH, in the second equation, both exist with the three key compounds in the same reaction medium. The underlined iodine and water react 1 mole to 1 mole in the Karl Fischer reaction and are consumed in equimolar amounts. The weights of 1 mole of iodine and water are 254 grams and 18 grams, respectively. Thus, you will understand that when you observe the weight decrease of iodine, you can calculate the weight decrease of the water. Dr. Karl Fischer noticed this and announced his analytical method for calculating trace amounts of water. This reaction is now called the Karl Fischer reaction. After further investigation, two methods of Karl Fischer titrations were developed and are used now. One is called volumetric titration, and the other is coulometric titration. I will describe them both in detail in the following slides. First, the analyzer for volumetric titration is an automated instrument based on the original glass analyzer that Dr. Karl Fischer formerly assembled himself. The main compartment is a sealed glass flask which contains methanol as a solvent for samples, and it has a detection electrode inside to detect the oxidation-reduction potential of the inner solution. It is attached also to a glass burette filled with the Karl Fischer reagent for titration, and the titration operation is done manually. In the volumetric titration analyzer nowadays, the titration procedure is automated. Two reagents are needed in this volumetric titration. One is the Karl Fischer reagent that fills the burette, and the other is the dehydrating solvent poured in the main compartment. The role of the latter dehydrating solvent is to dissolve samples and to extract water from the samples. We provide you with many kinds of dehydrating solvents that suit different sample characteristics, most of which contain methanol as one of the key 5 chemical compounds in the Karl Fischer reaction. When you dissolve your samples in the dehydrating solvent, methanol extracts the water inside the samples into the reaction solution. In other words, 2 chemical compounds out of the key 5 are ready to start the Karl Fischer reaction. The other 3 chemical compounds are titrated into the reaction medium as the Karl Fischer reagent, which consists of iodine, sulfur dioxide, and a base in appropriate solvent, and the Karl Fischer reaction finally occurs in the main compartment. Regarding the reacted water contents of samples, these values are calculated based on the changes of the iodine concentration, measured with the detection electrode. The optional back titration, which is usually practiced by pharmaceutical researchers in accordance with the Japanese pharmacopoeia, is explained on page 46 of the technical manual. Next, I will explain coulometric titration. This analyzer is developed for the purpose of measuring much smaller amounts of water inside samples. A sealed glass flask, called the anode chamber, is used as the main compartment, and 2 reagents, one an anode solution and the other a cathode solution, are used in this titration. The latter cathode solution fills the inner cathode chamber in advance, the cathode of this analyzer, is actually the platinum net installed in the cathode chamber, and the opposite platinum net at the outside of the cathode chamber is the anode of the analyzer. In our Karl Fischer reagent products, Aquamicron AX series are anode solutions, and Aquamicron CXU series are cathode solutions. The A in AX stands for anode, and the C in CXU refers to cathode. Though two kinds of reagents are used in coulometric titration as well as in volumetric titration, the contents of such reagents are different from each other. The anode solution in the main compartment, the anode chamber, consists of iodide anion, I-, sulfur dioxide, SO2, base, and methanol. That is, 4 of the 5 key chemical compounds needed for the Karl Fischer reaction already exist in the anode solution. When you inject samples into the anode solution, the water inside the samples is extracted, and all the 5 key chemical compounds needed for the Karl Fischer reaction gather in the main compartment, except iodine, I2, although iodide anion, I-, already exists. In order to generate iodine, I2, from iodide anion, or I-, the platinum net anode at the outside of the cathode chamber is used. When the anode deprives electrons from iodide anions, in other words, oxidizes iodine anions, iodine, I2, is generated at the surface of the anode, and the Karl Fischer reaction finally occurs in the main compartment. That is to say, necessary and sufficient quantities of iodine are being made electrochemically from iodide anions in coulometric titration, although an excess amount of iodine initially exists in volumetric titration. Such an electrochemical reaction, as an iodide anion oxidation reaction, can be controlled minutely. This is the reason why coulometric titration is suitable for measuring much smaller amounts of water in samples. Regarding the roles of the anode solutions, these solutions dissolve the injected samples and extract the water from inside the samples, but also work as a Karl Fischer reaction medium. There are many kinds of dehydrating solvents for volumetric titration in order to correspond to various kinds of sample characteristics. For coulometric titration, on the other hand, we provide basically only 2 kinds of anode solutions. One is for general use, and the other is for ketones. This difference of solvent variations leads to differences in applicability between these 2 titration methods, depending on the characteristics of the samples. Single-solution coulometric titration, in which only 1 solution, 1 reagent, or 1 electrolyte is needed, has already been developed. However, I would like to point out that a specified cathode chamber is necessary for single-solution coulometric titration. Please refer to page 197 of the technical manual for information about the optional single-solution coulometric titration. Now, let's move on to the detection principle. This refers to the detection method of the polarizing potential at a constant current. Here is the glass-made detection electrode, at the bottom of which 2 platinum poles are attached. When there is a constant electric current, these 2 poles become polarized as plus-charged and minus-charged respectively, because they are not connected directly by an electric wire. The electrical potential difference between these plus-charged and minus-charged poles is the voltage, which is the power source to cause an electrical current. Thus, the voltage values vary according to the ease of running the electric current. The detection method of the polarizing potential at a constant current is basically the way to detect the varying voltages at a constant current. Let me next explain how to run the electric current between the 2 unconnected poles. When these 2 poles become polarized as plus-charged or minus-charged, and they are able to accept electrons from the surroundings or donate electrons to the surroundings, the electric current flows. In other words, the electric current flows when the 2 poles are surrounded by chemical compounds that can donate or accept electrons. Remember that to accept electrons means to be oxidized, and to donate electrons means to be reduced. Iodine and iodide anion in reaction scheme A actually work in parallel to the tetravalent sulfur and hexavalent sulfur working in reaction scheme B. This sulfur is supplied from the reagent solution as sulfur dioxide. The reversible, in scheme A, means that the oxidation and the reduction, the acceptance and the donation of electrons, or the right side and left side reactions, are both apt to occur easily, and that the electric current flows at low voltages due to such ease. The irreversible, in scheme B, means, on the other hand, that the right side, oxidation, from tetravalent into hexavalent sulfur reaction, occurs quickly enough, although the reverse left side, reduction, from hexavalent into tetravalent sulfur reaction, occurs only with difficulty, and high voltage is needed to run the electric current. I think you may understand the shape of the titration curve in this graph. Look at the relation between this shape and the reaction schemes A and B. While the x-axis and the y-axis, respectively, show the elapsed time of the operation and the polarizing potential, the voltage to keep the constant electrical current, the polarizing potential is rather low before the injection of water, because reaction scheme A works smoothly. However, once water is injected into the solution, it consumes iodine through the Karl Fischer reaction and stops reaction scheme A. From then on, reaction scheme B begins to work to run the electric current, and the polarizing potential rises because reaction scheme B is irreversible, and it is difficult to occur, as I mentioned before. The analyzer detects this potential rise and regards it as the commencement of the titration. During some period while the water that still exists in the solution consumes iodine, there occurs no reaction scheme A, and the potential continues to be high, shown as B in the graph. Soon afterward, iodine becomes able to exist little by little in the solution, in accordance with the water consumption by the Karl Fischer reaction, because the iodine is supplied into the solution constantly by the titration of the Karl Fischer reagent through the burette in volumetric titration, or by the electrochemical formation at the platinum anode in coulometric titration. Reaction scheme A begins to work again at this step, and it makes the polarizing potential gradually fall, and the potential returns to the initial level at last, where reaction scheme A works smoothly again. The endpoint of the titration is determined when a slight excess of iodine can remain for a while, a 30-second duration, for example, in volumetric titration. An appropriate deviation range of the potential or the electrochemical reaction speed is set up to judge the endpoint in coulometric titration. In the next two slides, I would like to show you how to determine and calculate the water content in samples. Firstly, in volumetric titration, where the Karl Fischer reagent in the glass burette is used for such titration, the potency of the reagent is determined in advance. The unit of the potency is milligrams water, H2O, per milliliter, and the potency means how much water there is when 1 milliliter of this Karl Fischer reagent is consumed in the Karl Fischer reaction. It means, in other words, the weight of existing water in the milligram unit titrated by 1 milliliter of the reagent. I would like to explain potency more specifically in the case where the reagent potency is 3. This reagent is formulated such that 1 milliliter reacts with 3 milligrams of water, and thus it contains, in 1 milliliter, 42 milligrams of iodine. The volume of the reagent consumed in the titration is defined as the titer, and the unit we use is the milliliter. The weight of water in the sample is calculated when we multiply the titer by the reagent potency, and the concentration of water is calculated when we divide the weight of water by the weight of the sample. This procedure is shown in the equation at the upper right of this slide. In volumetric titration, the reagent is titrated dropwise into the reaction compartment intermittently at an irregular speed, quickly in the earlier period and then more slowly until the end point. The fluctuation of the titration curve is caused by the imbalance between the titration and the reaction speeds. When the titration is faster than the reaction, the polarizing potential falls, and on the other hand, when the titration ceases and the reaction still proceeds by the remaining water, the potential rises. The fluctuation width becomes smaller until the curve becomes a steady line at the endpoint, where the water inside is almost consumed by the reaction, and a slight amount of iodine remains. The endpoint is determined after the 30-second steady state, which we call n-sens, and then the titer for the calculation is fixed. You may understand that there can exist some slight error in this procedure to fix the endpoint of the titration, and thus volumetric titration is less suitable for measuring trace amounts of water than the coulometric method.